Hello there. We are going to have a good problem today. So welcome to another problem session. And this problem is going to be moderate to advanced topic. But even introductory people can actually get some out of it. We are going to cover some basic concepts in polarized material, electrically polarized material. Okay, so say you have plastic which is not, this is uncharged. I should have written uncharged. Okay, so this uncharged plate lies between two equally but oppositely charged metals. So here this is metal, and this is also metal. So the faces that face each other of the metal, they have opposite charges, and because these plates are infinite extent, we are going to talk about density of charge is this is like so many coulomb per meter square. Okay, and same here, coulomb per meter square type of density, right? We want to know in this situation, if plastic has a electric susceptibility given by this chi sub E, and haven't defined what chi sub E is, but if you know the definition, it's great. You understand the problem. As we try to do the problem, we're gonna learn more about this. Okay. So answer can be, question is about what's the potential difference between here and here. Like if I attach a voltmeter, the plus end of the voltmeter this side, so what will the voltmeter read? Okay, in this situation, when the plastic is there. When the plastic is not there, it will read different than when the plastic is there. So we are going to find what will read in terms of given. So this is given, this is given. In some other problems, the voltage is given and you can find the surface charge density. But we are going to have a charge density is given and we want to find the potential difference. Hope this question is clear to you. If you want to do it, go ahead and do it yourself. You know how to do it. What you might need is, as I was saying, what is electric susceptibility? So this is a background material you need. And you also need that at the boundary, at the surface of a polarized material, P is called polarization, and surface charge density can be obtained from there. Electric field, also if you have two plates, a positive plate and a negative plate, infinite in extent, and you want to know what's the electric field will be, that's the formula for electric field. Done this some time ago. And then if I know the electric field between negative and positive plates, if I know all the points, then I can go from, say, from negative place to, I can do this integral from a point here to point here and have a minus sign there, and that will give me the potential difference. That's the answer I'll get. So I need to know electric field all the time, all over the place. Okay, with this background, let me go over some of this background. Then I'm going to erase this and come back to it. So the background, let's see, if I have a polarized material, so let's not think about this problem. So this is some background. Okay, so if I have a material here, it can be polarized because the molecules themselves are polar, like water molecule, and they're locked in somehow. So it's polarized, maybe it's polarized minus plus like that, and the next molecule is minus plus like that, and minus plus like that, and so on and so forth, right? So minus plus like that. So you can see that this has a little p of each molecule. So if I go in this area at some point, say some point x, if I go sub point x, at that point I can say what's the density of dipole moments. So you can say, so density of dipole moments. It's kind of like a when you say density, if you think of density of a material is mass over volume. So this is, you can think of density as density of mass. That's what you are familiar with, and that's like just how much mass I have and how much volume. So this will be how much dipole moment I got. So if I add up all the dipole moments in this little volume and divide by the volume, so that's kind of density or dipole moment density. This quantity may be same everywhere or vary from place to place. So this would be called, this is called polarization of the material. This is the definition of polarization. And if I do it at centered about point x, at that point x, so this is polarization at x. So if you follow this thing, this can be polarization can take place because the molecules themselves are polarized. If that's not polarized, then another way can be material is not polarized. However, if I have some external electric field, so there was some kind of electric field going through here. These electric field lines of some other charge. There's some, maybe some here, there are some charges here and positive charges, and some over here negative charges, you know, so it's going from positive to negative charges, and the material is over here. So in that case, what we're going to see is if I go at a point over here, now the molecule over here will be electric field will pull the charges, you know, so the molecule will become minus and plus. So this is like induced dipoles, and these were like a permanent dipoles. So I can define the same way. So at this point x, I can define polarization at x is sum of this P over the delta V. Let's call it delta V, small volume. So just take a small volume here and say what's the dipole moment there. Okay, turns out the more the electric field is here, whatever the electric field is, a net electric field. So whatever the electric field is here, so electric field at that point is x, not external but the net, because these dipoles will create their own electric field. So this over here will be the electric field from all the charges got separated. Okay, all the dipoles got separated from them plus this outside. So this is the Ex is the resultant net field at x. Then if I look at how much polarization I'm going to get, it's going to be proportional to the electric field. Another thing to notice here is that polarization, this is the negative, this side is negative, this side is positive of the dipole. So the polarization is in the same direction as the electric field, right? Now this is for a material that is not like a crystalline material. if you have a crystalline material, polarization may be in a different direction than the electric field. So we're just going to be very simple. We're going to say just the magnitude will be proportional to that. So when it's different, then this will be like if this is 3 EX, EY, EZ, then this will be 3 by 3 matrix to say how the different electric field relate to the polarization. But we're going to not worry about that complication. We're just going to say polarization is proportional to electric field. So if I look at this two, that's how we define the proportionality constant. By this comes for convenience, and you can say balancing the units. So P at X is equal to epsilon naught, and the proportionality constant is what is called electric susceptibility of the material, and E at X. Okay, it's going to be very important. So this is so net electric field at X, net at X equals to E from this external sources. So E from external sources plus E from all these charges that has got E induced. Okay, electric field from the induced charges. And this thing is what's proportional to epsilon naught chi E 1 over this times polarization. So it's going to be, for us, it's going to be like that. This is proportional to that, not this guy, okay? This is a very big confusion. People think induced is proportional. No, this actually this is the net thing, and that's proportional to that. And so we were going to use this, okay, in solving this problem. Another thing that we would do is we would say that when working with this system here, the inside polarization is this P value at any point inside this plastic will be same. It will be same everywhere. If it's same everywhere, then you can see that at the surface, these charges at the surface on this side are all plus, and then inside guys kind of balance out, inside guys cancel out. You might say their effect is canceling out, but the outside, just at the surface, this side will turn out to be pluses, and this side turns out to be negative. Over here, the same way, this there will be sliver. There will be sliver of the very surface material. This side will be negative, and this side will be positive. And inside, because molecules are very next to each other, and if it's uniform inside here, if uniform, then this inside can be considered to cancel each other out, and there will be no extra charges left. But outside, at the surface, there will be some outside charges left. So let me erase so I can redraw. Okay, so what we're going to have here is induced charges. This surface will have a induced charge with sigma induced, and this is going to be a plus, and then on the back side, this surface will have a minus sigma induced, and it will be related with the polarization in this manner. So over here you can see the electric field is originally, let's draw original electric field. Original electric field is going from here through here all the way here, right? So this is the electric field. This was the E external, and you know E external will be given like that because you're plus sigma minus sigma. And so let's see if I use, because I'm gonna integrate from let's do it out this way. Let's call this z-axis. So electric field, original electric field E external is going to be sigma over epsilon naught and unit vector k hat. K hat is in that direction. Okay, so this, you always, whenever writing electric field, it's always good to keep the direction together. Okay, here it's kind of one dimension, so probably not going to be that problematic, but later on or in another situation it becomes problematic, and so you should always keep the direction. Okay, so now let's see how much will be this guy. So if I look at inside a point inside, so this is like, this is A and this is B and this is C. So in here, so look at a point inside, let E net equals to be the electric field, right? Then what's E net's going to be? Then P, then polarization P. So the E net is going to be in the k hat direction. So P is also in the k hat direction. P polarization vector I can write down is epsilon naught chi E net vector. Okay. So okay, then if you look at these charges will be simply this p vector dot n hat. So on this surface, on the right surface, the n hat is that way, n hat on the right surface, and on the left surface the n hat is that way, because n hat is coming from inside to outside. So you can see over here is same direction E net. So on sigma induced is equal to, on the right surface, let's call it, is going to be plus epsilon naught chi E net, and on the left sub sigma left surface induced equal to minus epsilon naught chi E net. So what's the E net going to be? Well, what's the net electric field at a point, at this point? Well, it's going to be electric field from these charges, the external electric field from these induced charges. As a case of name, these induced charges are also called, bound charges. Bound charges, just so you know. They seem to not, they won't flow just like electron, they're just bound to the atoms, okay? Atoms of this non-conducting material. So if I give you, these guys are like just plates, a positive charge plate, negative. So if I give you this, then I can use this formula again. So this would mean the induced part, E induced part, is actually going from positive plate to the negative plate as in the minus k hat direction, and it's one of these charges is equal to epsilon naught chi E net over epsilon naught, right? So this is like a sigma over epsilon naught. This is sigma b over epsilon naught. Epsilon naught cancels out. So let me clean this up a little bit. Okay, so now we can actually get the answer fully looking at electric field at this point. So let's call this point X again. So electric field at X is electric field from these charges. I'm going to call it A and B, and I'm going to call it this end C and this end D. Okay, so electric field from AB system plus electric field from CD system. So this is the net electric field. This is the net. So that there's some E net in the Z direction. So E net K hat, and AB was just sigma over epsilon naught K hat from the way it's written down over here, and this is going to be negative chi E net K hat. So we can just bring this on this side. So E net, I can solve this E net times 1 plus chi E is sigma over epsilon naught. So the net electric field, which is inside, so net at X is equal to sigma over epsilon naught times 1 plus chi E. So so we found answer. So if I'm from so between A to C and C to D and D to B, so we can write down the electric field now. So electric field between A and B is electric field. So this is Z axis. So E at E is equal to, let's call it some EZ K hat, and EZ depends on where I am, and this is Z between 0 Z 0 to A, and that's sigma over epsilon naught. And if I'm between A, Z, B, this is sigma over epsilon naught 1 plus chi E, epsilon 1 plus chi E, and between B, Z, C, I'm back to sigma over epsilon naught because chi E is yeah, so we're back to epsilon naught. Okay, just to recap, so we found the net electric field if you're in this region is this, if you're in this region is this region is this, right? So what's the potential difference between these two plates? Well, we have a potential difference formula between any 2 points. So take a point, let's call it point A, and we can call this point capital B. So from between A and B, what's the potential difference? So I want a VA minus VB. So it's integrate minus B to A E dot DL, right? So this is like on the positive plate, this negative plate. So I go from the negative plate to the positive plate. So this is the reference to where I want. So this kind of like a reference to where I want. So reference to this integral, right? So that's the integral. So we need to say what's the DL, what's the D. So we're going to take a, so we're integrating from here That's the path we want. So if you look at what the dl is, say this is a z and this is z plus dz. So if you okay, so I'll leave this for you to actually set up the integral. There's a little bit of trickery here. So you can set up dl equals to like a dz k hat and e equals to ez k hat and do this integral. But you probably have done this integral in the case of a constant electric field, sigma over epsilon naught, the plus or minus, and you know this leads to between point A and point B, so this is A and B, so VB minus VA is simply going to be sigma over epsilon naught times this distance d. So this is like electric field, right? So if you know the electric field in the constant electric field, so E0 is delta V over D. So if you remember that, then you know all of these constant electric fields. So between say A and this is say point C, this is point D. So this whole thing will be VA minus VB will simply be VA minus VC plus VC minus VD plus VD minus VB. So in each one of them, I can actually write this down. So this is delta V between positive and negative plates. That's going to be equal to VA minus VC, sigma over epsilon times the distance here, sigma over epsilon times distance A, plus this is the electric field in this region, epsilon naught 1 plus chi E. 1 plus chi E is also a dielectric constant. Sometimes you write it for combining different symbols rather than write two terms here. You can just write one term, and this is going to be B minus A, and then this will be sigma over epsilon naught C minus B. So you can see all of this written in terms of this sigma alone. Okay, so you could take it out, sigma over epsilon naught, and you have A plus C minus B. So these are the spaces here and here, this thing, and then you have a B minus A over 1 plus chi E. Okay, so we have here delta V. Okay, sometimes, so this is the answer our problem, okay, but sometimes instead of giving this sigma as a starting point, we are given this as some kind of V naught. So like this, we are given these two plates and connect to a battery and wait for a long time, and this is voltage V naught. So this charge up and this charge up, right? So this charge up plus sigma 0, this charge up minus sigma 0, and you can say if this distance is C, then you know that electric field here will be equal to pointing from positive to negative, is going to be V0 over this distance C, which is also equal to sigma 0 over epsilon naught. So this is in this case, right? Now we bring this. So then this is not the case because it changes different places, and then this not the case. this becomes some new sigma, and this is minus sigma naught, and this sigma is what that is. So, so if you're given V0, you will come all the way here and get your sigma, right? So you can get a sigma given V0. I can get a V0 given sigma. So this is, you get sigma if V0 is given as a starting place. You will still come out here like this. You hypothesize that there is some sigma and then work out the way we worked out, okay? You get V0 like we did here if sigma is given as here, okay? I just wanted to talk to you a little bit about subscribing to this channel. If you like very straightforward discussion of the physics using the language of mathematics that we're using, which is the language of physics, then you can subscribe. You can hit a like button. If you want more of this kind of stuff, this approach to physics, introductory physics, you may want to go there and check out that website. Okay, that's the website I maintain. My approach is that rather than give you a very mysterious explanation, physics is, once you use the mathematical language, it's rather straightforward. It takes a little bit getting used to the approach of using mathematics to describe physics, but that's actually the least confusing. You don't really guess too much. You have to guess sometimes in terms of the orders of magnitude, if some things are more important than the other. But other than that, guessing, you're not wholesale using formulas for the sake of using formulas. You're just building on some mathematical, building on some physical, experimentally verifiable laws, and then using some kind of modeling and mathematics to get to your answer. So that's a I call it very straightforward approach to physics. Hopefully you enjoy this. Well, take care. Bye.